Okay, so we're going to cover Chapter 12 a little bit, and Chapter 12 is on more editing. Topology. Topology is how that it's the relationships between objects in the GIS, and whether things share a coinciding boundary, whether they overlap, underpass, overpass, etc. So one of the first things we talk about is rules with topology. That's things like adjacent polygons must share a coincident boundary that exists at the same for both. There are no gaps or overlaps between adjacent polygons. Here are some examples of an overlap, where one polygon overlaps another, and a gap where space that shouldn't be there is. The polygons on the right are how it should actually look. Two lines should always end on other lines. Failure of two lines to meet is called a dangle. Undershoots occur when one line is not quite long enough. Overshoots when it goes past the mark when the topology is correct. Lines that's supposed to intersect like that. The other thing that happens is that there should always be a node when things cross, if they actually cross. And so if you have an intersection, four-way, then you should have a node there. If it's not, then it shouldn't be one. Nodes should exist only where three or more lines intersect. A node where only two lines meet is called a pseudonode. In other words, if you have a point in a line, it's a pseudonode. Lines or polygon boundaries should not cross over themselves and form loops. There should not be duplicate copies of any points, lines, or polygons. It's another topology. So how severe are these issues with topology? Many are undetectable. The errors don't show up in the maps, and they don't impede any kind of analysis. Some are minor annoyances, errors that show up when you zoom in, and they make your maps look kind of crappy. Some are analysis stoppers because they cause all these hundreds, if not thousands, of tiny little polygons that all have to be analyzed as well. And so they can just really create problems. Or maybe you're running a tool like some sort of a utility network, and they literally make it impossible for things to work. Legally, they're a big issue if we're talking about things like property boundaries and parcels and that sort of stuff, as far as like what if things overlap, who actually owns what, who pays taxes on what. Sometimes topographical errors reflect actual real-world situations. This is a classic example of a dead-end street, or a cul-de-sac, or overpasses and underpasses. In these situations, even though they don't apply to the standard topological rules, they are correct topology because they meet the concept of logical consistency, which is the fundamental question of topology. How well features mimic relationships in the real world? That's what it is. Does the interaction between features in the GIS make sense in terms of matching the interaction that exists in the real world? So when we try to do this, there's two basic models that we work with in GIS. The first is a spaghetti model. This is a model that doesn't have topology. Each individual item is just that, an individual item. Shapefiles, geodatabase, feature classes, it doesn't matter. They're simply placed in the GIS individually, and there's no rules for how they interact with one another. There's no way to test for logical consistency. But you can use simple tools to create consistent features like snapping and autocomplete and that kind of stuff. But the user, you, takes complete responsibility for creating correct features when you're editing stuff in a spaghetti model. In a topological model, you store topology, and this allows settings of rules governing topology within and between layers. So you can make things have coinciding boundaries. You can make things not have pseudonodes and dangles. You can make things not have gaps and overlaps. And then you can run these rules and test, and it'll identify areas where these things are occurring, and then you can complex polygon topology. Here's an example of something that can be really difficult when you're digitizing. So there's two methods that Price talks about. The first is divide and conquer. You start by creating a square outside boundary, and then use the cut polygon tool, and you one by one carve out each of the polygons. The second method is called the add territory, and you use the create new for the first polygon, and then autocomplete for the most of the others. In other words, so you'll start drawing from one and then add the next one into it, and then let autocomplete close those things up. So what do? Well, close off and do 4 and 6 separately, then merge them would be one option. You can attach 3 to 2 before you do 5. You can do 11 right after you do 7b. You can do 8b and use the clip to remove it or erase it. If there's an overlap, there's lots of different ways you can do it. And it all comes down to figuring out what you want to do. So like with that 8b, you can make that polygon, and when you make the 8b or 8a rather, it's going, either one of those will include that, so you'd have to cut that out. So that's what they're saying about using things like clip to remove it. Combining and buffering features. Merge is a really helpful tool sometimes. It combines features and attributes. It removes common boundaries if they're adjacent. However, sometimes pieces may end up being that are adjacent or disjoint. It can create problems. You got to figure out which one's your target, which one's your source. Its attributes will be assigned to the merged feature. The source feature attributes will be eliminated. So you need to make sure you're joining things the way you want to get the data that you want at the end. Union is very similar. Creates a new feature, leaves originals unchanged, but it doesn't do squat for your attributes. Intersect finds common areas between features. Creates a new feature, again, nothing with attributes. Buffering, you can use points. You can buffer points, lines, or polygons. The target layer determines the output type, lines or polygons. You specify the distance in map units. Stream digitizing. If you're really good, you can click each vertices with the mouse. But if you want to stream it, you enter a value automatically every time the cursor moves a certain distance. And so once you set it up and you get started, as you begin to move your mouse around, as it moves, once it moves a certain real distance on the map, it throws down another point. Point-to-point advantages provides best control, especially with the mouse. It's not easy to smoothly follow a line with a mouse. That's a problem. But there's less fixing of spurious vertices later. It's more efficient data storage because you don't have as many vertices. The more vertices that you have, particularly when you're dealing with long straight lines, the more complicated it makes the feature, and the more difficult it makes any kind of analysis that you do with it. Streaming advantages, it's really fast if you're very smooth. But it can create problems. But it does maintain consistent feature resolution, which is an advantage. Stream tolerance. Prior for streaming, the user sets the minimum distance between the vertices. As the cursor moves, a point is added when a vertices is covered. A tolerance that's too small collects too many. One that that's set too large misses things. And so the one in the top looks almost like a solid line. So at the bottom, you missed parts of the feature because of the way it did it, and the one in the middle is probably a good compromise. All right, so a little bit more about editing. How do you change stuff? Well, to modify a feature, you use the edit tool to select the feature, and then change the task to modify the feature, and the sketch appears, and then you can click and drag and move vertices around. You can open the sketch menu, you can add vertices, you can finish the sketch when you're... Okay, let's try that one again. So you can use the reshape tool to change shape. You can turn on snapping. You could add new vertices and then have it go to those ones to change the shape like you see here. You can flip lines, so every line has a direction to it. It usually doesn't matter, but for some things like roads, it can. And so if you have a road or a stream or something like that that's going one direction and you want to send it the other way, you can simply click on it and use the flip function. Multi-part features are features that form by a collection of several simple features that may be disjointed. In other words, they're not physically connected, but they're all part of the same thing. Classic example are the 7 islands that make up Hawaii. You can also construct points, place points along a line by distance, any number of things there. You can move an exact distance from the editor. Just hit the move thing, tell it how far you want it to go, and it'll go that far. Copy parallel is another one. How do we prevent errors? Basic editing or avoid topological errors to begin with. Use tools like snapping and splitting lines and autocomplete and the cut polygon in the clip, and then use map topology and shared editing. Avoid dangles using things like snapping. You can avoid improper intersections by splitting lines and snapping the vertices. You can avoid gaps and overlaps using the autocomplete tool. Clipping works wonderful to get rid of stuff. Create polygons inside of other ones in different ways. How do we use map topology? When we edit in ArcGIS, basic user can create a temporary topological association between layers. It's called a map topology. Map topology allows features to be shared with shared boundaries or nodes to be edited simultaneously. And so this is big because what it allows you to do when you have multiple features and you move vertices and there are multiple features whose boundaries are made up of that, they're all edited simultaneously. Cluster tolerances is a maximum distance things can be moved during edits. Set it too small, nothing happens. Set it too big, miss things. How do you do it? There's a tool for it, like everything else. Open the topology toolbar, the map topology tool, choose the layers that you want to work with, and set the tolerances that you need, and everything will work. You can modify edges and reshape and show shared features. These are all different kinds of tools. Going in and editing the topology, again, it's pretty easy. Moving shared lines, moving a shared node, sketch geometry options. Again, there's tons of these things. The problem is you'll never remember how to do all these. But as you work through the teaching tutorials and the lab exercises, you will use these. And then hopefully someday when you need to, it won't be like trying to translate hieroglyphics into smells when you try to actually use these tools again. Modifying a shared edge. Select edge with topology edit tool. Click the modify edge tool, move it, add it, finish it, do whatever you need to do. You can also reshape it. Talk a little bit about planar topology. Topology includes rules that define all these relationships. Things that violate the rules are considered to have errors and need fixed, and so it allows you to run tests to see what needs fixed. So you set up the rules, that you want. ArcGIS has all kinds of rules. You just need to figure out which ones you want to use. You do have to have a standard license. So what are some of the rules we're looking at here? Topology rules establish how features should be spatially related, and so no gaps or overlaps, and things having to share coinciding boundaries. All of these are ones that you could apply. Some examples of the rules and how they're set up. Once you implement them, the topology rules are defined within the feature data set. One or more feature classes in a feature data set may participate in a topology class, and there's special tools to do all this. And then validation is used to find and mark errors for editing. So it goes through, applies the rules, identifies everything that doesn't comply with the rules, and then you get to go fix it. Different kind of rules that are out there. There's a bunch of different ones. Here are a bunch of the examples of polygon rules. You should make yourself familiar with that list. If I'm feeling particularly vengeful, there could be test questions from that. Same way with these rules. You should have an idea of what some of the topological rules are for lines, endpoints, and multiple classes. So how do we validate? The first step, software checks all the features. Things that are close together with clusters, it fixes automatically. Things that are outside of the cluster range, it flags and lets you worry about. Again, set your tolerance too low, nothing gets fixed. Set it too high, it changes stuff you don't want changed. Cracking and clustering. Validating topology passes through two stages, cracking and clustering. In the cracking stage, vertices are created along edges that fall within the cluster tolerance of an existing edge, vertex, or endpoint. In the clustering stage, the endpoints and vertices that fall within the clustering tolerance are snapped together. So the first thing we do is create these things. Second thing is we identify ones that are within the right distances, and then we pull them together. Ranks control which feature will be moved during clustering. Lower ranked features will be moved to meet higher ranked features, and so you can set sort of an order of importance as to which ones are moved to meet which ones. How do you create planar topology? You go to the new topology tool. In catalog, it's pretty straightforward. Classes and ranks. Within the topology, you can set those up and do all those things. And then how do you add the rules? Once you set the class up, then you apply rules by simply going down to the list and seeing what's there and adding the ones that you need to each layer that needs them. And once you're done, you can validate it. And then it'll go through after validation. Errors that are not fixed but clustering are marked for manual editing, and they're stored in topology and can be displayed. And here you can see what the errors look like. Again, so toolbar, this is where a lot of this is done from. As far as the errors and how you can do that, you can go into the show rule description and see what's going on. You can inspect individual errors. You can change and control the selection process. You can set up exceptions. Dirty areas are areas that have been edited, and they're called dirty areas when validation is run. Only dirty areas need to be updated. This saves time when validating large feature classes after minor edits. In other words, things that were okay before, it doesn't check again. Things you edited, it checks again. So how does the editing process work? You create topology, you validate topology, you edit topology, you validate it again, fix any new errors and validate it again. You wash, you rinse, you repeat. You wash, you rinse, you repeat. It's just like shampooing your hair until it's clean